So let's look at some of the results of this model. So this paper, Chirokova and Webster, which is referenced extensively, are results from that J. McCreary model that we just looked at, 2.5 layer model. So this is showing heat transports in the Indian Ocean, annual cycles of northward heat transport across the equator. So how much heat is being transported in and out of the North Indian Ocean north of the equator, the net flux into the North Indian Ocean, and changes in heat storage. So we'll see an equation where we will see these terms. B is latitude time section of the annual cycle of northward ocean heat transport in the Indian Ocean, and C is latitude time section of the annual cycle of northward flux of heat average through the troposphere. So are the ocean transports and the atmospheric transports pretty close to being balanced? It turns out that they are. Okay, so look at the meridional ocean heat transport here, QV, and the total heat storage, and this is the meridional atmospheric latent heat transport, and the surface heat flux is coming in, the sum of short wave, long wave, sensible, and latent heat fluxes. So the heat storage here is a combination of the atmospheric surface flux forcing and the heat transport. So you have heat flux coming in, especially during MAM. There is weak winds, net heat flux. It doesn't quite go to zero. At the end of the year it turns little negative, but throughout the year you have heat going into the ocean, and meridional atmospheric latent heat transport is going to correspond to the moisture transport, which is obviously related to the winds, monsoonal circulation themselves to the north of the equator, and you can do the Ekman transports using Coriolis and so on, and you have monsoonal winds bringing moisture, as we saw before, and winter monsoons taking moisture out of the North Indian Ocean. The meridional ocean heat transport, on the other hand, is kind of balancing the sum of these two, creating an ocean heat storage. So you can see that during the monsoon season, as we will see, there is southward transport out of the northern Indian Ocean across the equator. During the northeast monsoon and intermonsoons, you have northward heat transport into the northern Indian Ocean across the equator. So we'll see that in a little bit. If you look at that distributed latitudinally and season wise as before, again you see that there is heat flux into the northern Indian Ocean centered around the southern hemisphere. We'll see other pictures soon as well. And again, maximum southward heat transport is around 10 to 15 south, and during the monsoon season it is strongly southward. Okay, so that's something to remember. This will be used to argue the quasi-biennial time scale. Meridional atmospheric latent heat flux, again showing the flux into the northern hemisphere from the southern hemisphere, because you are evaporating and bringing all that moisture into the monsoon domain. During the winter monsoons, you obviously have southward transport of evaporated water vapor. Okay, the split of the heat storage can be done into two components. One is that you assume a layer of, let's say, something like water above the 20 degree centigrade isotherm, and then you follow its seasonal evolution, and then you look at temperature change above that level. Okay, so you are looking at heat content change above the 20 degrees C isotherm, which we can think of as the thermocline. And the other component is how the thermocline depth itself will change, looking at the seasonal evolution of the average temperature above it. So you are taking the average temperature above it and look at how the volume of the water above the thermocline is changing. So it's a simple split, as you can imagine. These two together will determine how the temperature and the depth of any given isotherm are changing in terms of determining the heat content of the upper ocean. people argue in the Atlantic and Pacific Oceans as 20 degree C isotherm being a good indicator of the thermocline, the temperature gradient change, whereas in the Indian Ocean it's a bit more weakly stratified, so sometimes people use the 24 degree isotherm instead of the 20 degree isotherm. So you can look at that annual cycle as well in terms of the heat transports in petawatts, which is typical 10 to the 15 watts. So this is heat storage in the northern Indian Ocean again, and you can see that the heat storage by the change in temperature above the isotherm and the heat storage because of the depth change itself are typically out of phase. So it depends on the wind driven transport versus the other terms that are creating the temperature change, and they are clearly out of phase here, but during the strong summer monsoon season they are in phase, both negative, so southward negative changes. This is the storage term, and then again they go out of phase as you go into later monsoon and intermonsoon to winter season. Okay, there is the heat flux into the North Indian Ocean again, and there is the heat storage shown again. So the North Indian Ocean is losing heat in the monsoon season and storing heat during the non-summer monsoon season. This is the main message you want to remember, along with the details of these transport issues. This is just showing the zonal heat transport across the equator and across 10 south, and you see the strong boundary current effect here and these propagating features that we talked about as Kelvin waves and the Wetke jet and so on. So that's the zonal mean. The story remains similar as before. Across 10 south, the East African coastal current that we talked about has strong northward transport throughout the year. Remember, it was going northward, merging with the Somali current north of the equator with the Great Whirl and the gyre, southern gyre, whereas in the winter months the Somali current is coming across and meeting the East Australian current. So that is seen here, and you again see these Rossby wave-like features now at 10 south with the zonal mean shown here. But if you integrate across zonally, you see that the boundary transport is essentially compensating for the broadly distributed interior transport in both across 10 south and the equator. Okay, so these are kind of the zonal distribution. So the zonal variability of the heat transports matters as well. Okay, so we will remember those and try to see what they mean for the coupled monsoon dynamics that we are interested in. Okay, so we have talked about Ekman transport being continuous across the equator, which has to be explained, and the seasonal heat transport and heat storage terms, which have to be considered in the context of whether they have a feedback to the monsoon, especially whether they can give the quasi-biennial or biennial timescale that seems to be present in the IOD and in the monsoon as well, and in many other features like the thermocline depth in the tropical ocean, Indian Ocean, even in the Australian monsoon and so on. Okay.